Hi folks, we saw in the last video that the way that you use a conjunction in your context is destruct. In this video, we'll learn, surprise, surprise, that the way you use a disjunction in your context is also a destruct. What happens ends up being a little bit different, but the methods are the same. Okay, let's start with an example. We'll prove, kind of a theme here, that or disjunction is commutative. If you know P or Q, then you know Q or P. Let's get started. Okay, so we know there are propositions P and Q, and we know HPQ that P or Q holds. And we want to prove that either Q or P holds. So intuitively, if HPQ is this disjunction, someone had to either go left and prove P or go right and prove Q. Now we don't get to know which. Maybe they could have done both, but in reality we'll only ever see one. So we don't know. What we can do is we can say, look, if we currently believe P or Q, let me just finish my proof for both branches, right? If I can finish it for either branch, then P or Q is sufficient to show whatever I want, right? If it works with P and it works with Q, then it works with P or Q, right? So here the idea is, well, to account for a disjunction in your world, in your context, in your assumptions, you just cover all your bases, right? To show that P or Q implies Q or P, we'll show it for P and we'll show it for Q. Okay, here it shouldn't be too bad. If we're in a world where P holds, well then we'll go right and we'll prove P. If we're in a world where Q holds, then we'll go left and we'll go Q. So what we need to be able to do is to ask, well, which world are we in? And destruct does exactly that. So we'll destruct HPQ, and here I've used an as pattern to name the subparts. Now, unlike conjunction, I've got the pipe in the middle, because these are really two different worlds. The pipe is sort of separating these two worlds. There's the world on the one hand where HP was proved, and there's the world on the other hand where HQ was proved. Right? So we have to ask, which world are we in? Let's do it. Destruct HPQ. Let me see which world we're in a world where P holds. Coming soon to theaters near you. Okay, so HP is a proof that P holds. Nice. So we're in that left-hand world where P holds. So now we can say, well, great. To prove Q or P, we would need to be in a right-hand world. So choose the right path and apply the assumption, right? HP shows exactly what we need. On the other hand, if we're in the world where Q holds, well, fine. We just need to take the correct left branch because we were in the right world for P or Q. Now we're in the left world for Q or P. So go left, apply HQ. Brilliant. Now, just as before, rather than introsing a name and then destructing that name immediately, you can just write the pattern in intros and it'll work it out for you just fine. Brilliant. Okay, so now this has just done immediately the case analysis, and then the rest of our proof script is identical. Okay, I want to work one more example, just to show you. So let's see, for every natural number n, either n is equal to 0, or n is the successor of the predecessor of n. This utterance showed up at the end of day 11 in some of the quizzes, but now we see, okay, either a number is 0 or it's the successor of its predecessor. Okay, great. So I'm going to do it with this style. I like to, even though we'll never see the name n again in this proof, I really like to name it n prime just to remind myself that this n prime is different from the n that we quantified over. That's just me, though. If you wanted to write n here, I respect that decision. Okay, so let's look at the base case where n is equal to 0. So we have to prove, we have our choice, either that 0 is equal to 0 or 0 is the successor of the predecessor of 0. I'm skeptical on this one. That side is not looking good to me. This side, however, looks great. Okay, so let's say left, we have to show 0 equals 0. Well, that's true by reflexivity. Those are immediately equal. Okay, now we have to show either that the successor of n prime is equal to 0, unlikely, or the successor of n prime is equal to the successor of the predecessor of the successor of n prime. Some of you may be wondering why nat.pred shows up here. It's because we're starting to use some standard library definitions. Sorry for any confusion. Okay, I'm going to go on the right branch here because this side looks promising. I'm gonna run a simple to see if we can get rid of that pred. Perfect. Okay, now again, we're good to go by reflexivity, which means if I can spell it correctly, it means that we could have just done that from the get-go. Okay, great. So that's all I want to sort of show for disjunction. This is sort of a classic case, but using the destruct to destruct a natural number, and then using left and right to generate a disjunction, right? So there's a lot, we're starting to combine the tools that we have here. Okay, in the next video, I'll be talking about falsehood and negation. Looking forward to talking about that, and I'll see y'all soon.